Today we are going to look at exponential growth and exponential decay graphs. Exponential growth graphs. This is like how germs multiply in your body to make you sick. You've got one germ cell, and then it doubles to 2, and then it doubles to 4, and then doubles to 8, 16, 32, 64. Pretty soon you have a huge number. So you start small, you start with like one cell, and then it just explodes. So exponential growth starts really close to the x-axis, and then as it moves to the right, it gets larger much more quickly than a straight line. Some might say it gets larger exponentially because it's exponential growth. Exponential growth can also start really close to the x-axis on the bottom side and then move away from the x-axis down on the graph. If the graph starts on the left close to the x-axis and then rapidly moves away from the x-axis, that is an example of exponential growth. Exponential decay. Has anyone heard of carbon dating? Okay. All living organisms have a certain amount of carbon in them. When those organisms die, the carbon starts leaving the remains at an exponential rate. But you can look at how much carbon is left in a substance, like a bone that's found or something like that, and you can go backwards and figure out when that organism died based on how much carbon is left. So in this case, we start out with a whole bunch of carbon in our system, and then as things rot, basically, we lose that carbon. Trying to make this not look bouncy on here. So if it starts far away from the x-axis and then rapidly gets closer to the x-axis, that is an example of exponential decay. Exponential decay can also start far away from the x-axis in the negative direction and then get closer and closer. Notice in all of these examples, my graph did not cross the x-axis. The x-axis is an asymptote. Asymptote is a funny mathematical word that has far too many consonants for the vowels. And to say it, you basically say every single consonant. Asymptote. An asymptote is a line that the graph is going to get closer and closer and closer to, but it won't ever actually touch the line and it won't ever cross the line. So if you ever see like my graphs look like they touch the asymptote, if you were to zoom in and zoom in and zoom in, it would show that line getting closer and closer and closer, but never actually touching it and never crossing it. Okay. Originally, this was a calculator exploration, and we took the time to enter all of this in the calculator, but that just kind of is a waste of time. So here's the pictures from the calculator. The parent function, y equals 2 to the x. Notice this graph starts close to the x-axis and then rapidly moves away from it. This is an example of exponential growth. I'm going to take this function, y equals 2 to the x, and put this minus 4 in the exponent. Y equals 2 to the x minus 4. What happens to this point 0, 1 from the parent function when we put that minus 4 in there? Any guesses? Your voice can be on video, it's okay. It moves how? Right? 4. So in graph A, this minus 4 moved the graph right 4. Does that seem a little bit familiar to the other times that we've graphed functions? Okay. The plus 3 in the next graph, the point started here at 0, 1 and moved left 3. So that plus 3 moved the graph left 3. So what is the role of h in the equation y equals b to the x minus h? Plus h moves left minus h moves right. If it's in the exponent, it moves the graph side to side, left or right, and it's opposite. So plus actually moves left, minus moves right. The next parent graph we're going to look at is an example of exponential decay. And notice the difference in the number that's being raised. In this exponential growth, it was 2 to the x. In the exponential decay, it's 1/2 to the x. So if the number being raised to the exponent is a fraction less than 1, it's going to be an exponential decay function. It starts far away from the x-axis, and then it curves and gets closer and closer to the x-axis, but doesn't actually cross it, doesn't actually touch it. Okay, so that point is going to start at 0, 1. So I'm going to put 0, 1 in all of these graphs so we can kind of see how that point moved. In C, we're adding 3. And what happens to that point? Up 3. It looks a little bit deceiving because the point started at 0, 1. So the point was already 1 unit above the origin. So when we move up 3, if you're already 1 up 3 more would put you at 4. And D, it says -5, and that point is going to move from 0, 1 down 5 to 0, -4. So that one moves down 5. So what's the role of the plus k? Plus moves up, minus moves down. Now before we turn the page, I want to talk to you about the asymptote. In graphs A and B, do you see how the graph gets really close to touching the x-axis but doesn't ever cross the x-axis? These all have an asymptote, y equals 0. The graph gets really close to the horizontal line, y equals 0, but doesn't cross it. But when we move the graph up or down, do you see how in C it gets really, really close to touching this line, but doesn't actually touch it and doesn't cross it? And you might notice that that line has an equation, y equals 3. So moving the graph up 3 is going to move the asymptote up 3. In D, moving the graph down 5 is going to move that asymptote down 5 to y equals -5. So up and down movement is going to also shift that asymptote. And that will be something that's going to be asked of you, is what is the asymptote of each graph? So you need to look at how it shifts up or down to determine that. All right, next page, let's look at multiplying. In E, we're looking at an exponential growth function. You might want to jot down that the parent function for all of these is y equals 2 to the x. So in E, we're taking the parent function and multiplying by 3. And you'll notice it crosses the x-axis at 3 instead of crossing the x-axis at 1 like it used to. This graph increases more rapidly. So this is a vertical stretch. Some might describe this graph as taller or skinnier, more narrow. Imagine taking the graph, grabbing the ends, and just pulling it vertically and stretching it. It's going to increase much faster. In F, we're multiplying by 1/2. That's going to smush the graph and make it increase less rapidly. That would be a vertical shrink. Some might say the graph looks shorter or wider. It's like we smushed the graph. And what's happening in G? Flipped. It's also stretched, but most importantly, it's flipped. So the A is going to stretch, shrink, and or flip the graph. It stretches the graph when A is larger than 1, like 2, 3, 4, 5, etc. It's going to shrink the graph when A is between 0 and 1, like 1/2, 1/4, 0.7, 0.2. And it's going to flip the graph when A is negative. Okay, let's talk about some specific characteristics. The graph of A times 2 to the x has certain characteristics. So you might want to outline that this is the graph, this is the equation that we're talking about. Take a look at E, F, and G. In E, the y-intercept is 3. We multiplied by 3. In F, the y-intercept is 1/2. We multiplied by 1/2. In G, the y-intercept is -2. We multiplied by -2. So whatever that A is, that is going to be the y-intercept. The y-intercept is going to be A. This is incredibly helpful if I give you a graph and say which equation matches this graph. If the graph has a y-intercept of 3, you're looking for the equation that says 3 times something. So it's another way to pick out which graph matches. The x-axis is an asymptote. And here's the definition for asymptote written right above that. The domain is always going to be all real numbers. And remember, you can write the word all and then the capital R with a double stem. That means real numbers. The range is either y is greater than 0 or y is less than 0. It's greater than 0 when there's no flip. It's less than 0 when you have flipped the graph over the x-axis. So if that A value was negative, it's going to flip that range to y is less than. If there's no flip, if that A value is positive, the range will be y is greater than. And then a quick little recap. A is the stretch, shrink, and flip. H is side-to-side movement. Plus means left, minus means right. K is the up or down movement. Plus moves the graph up, minus moves the graph down. Okay, let's do number 11 together. Horizontal refers to side-to-side movement, left or right. That would be whatever is in the exponent. This one doesn't have anything added or subtracted, so horizontal movement would be none. Vertical movement. Vertical movement is how the graph moves up or down. This one says +4, so it's going to move up 4. And don't just write up, make sure you write up 4. Put that number in there, it's going to help you later on. The stretch is the number that's being multiplied in front. This is a whole number, 6, so it is going to definitely be a stretch. If you are multiplying by something like 1/2, it would be a shrink. If you were not multiplying anything in front, you would write none. Like take a look at number 10. Is there a stretch in number 10? No, there's nothing being multiplied in front of that term that has the exponent. Direction. Because there is a negative, this is a flip. The range and the asymptote are tied to the vertical shift. Because this graph moves up 4, the asymptote also moves from 0 to 4. And the range is going to involve the number 4. Because there was a flip,